Let us continue here. I have described to you revolutionary science now, and the next step will be, we had discussed that a little earlier, I think 2 weeks ago, the parallels between this phase of revolutionary science and pre-normal science, because there are similarities and dissimilarities, and I want to discuss these dissimilarities and the similarities of revolutionary science and pre-normal science, because you learn something about revolutionary science in this way. Now, revolutionary science, first of all, differs from pre-normal science in that there is a consensus about the significant anomalies to be solved. That's a very important point. In the face of pre-normal science, people even disagree about the range of problems that have to be solved, because the limits, the borders of the area are just not clear, and they depend in the way how you look at it. I described to you the problems of electricity theory in pre-normal science, and people differed in what is very important to be solved and what is not so important to be solved. That is different in revolutionary science, and of course the difference is that in revolutionary science originates out of a phase of normal science that was previously in place. And therefore, for instance, in the case of Bohr's model, it is absolutely clear that the new theory that comes after Bohr's model must somehow be able, for instance, to confront the helium model, the helium atom, right? Because that is something the theory couldn't solve, and it was absolutely clear it must be solved. So everyone knew this is an important problem, and a new theory should be able to solve the helium problem, right? That is because that results from the failure of the old theory, the old phase of normal science, to solve the problem, and therefore people know it's an important problem that must be solved. So this is one of the things that we have, so to speak, a consensus about the problems that must be solved, because they are the result of the failure of the former phase of normal science. There's a consensus about the significant anomalies must be solved, and again, a difference to pre-normal science, there is a consensus and a need to preserve or reproduce the results of an earlier accepted theory, right? Again, this is different from pre-normal science, because in pre-normal science you don't have anything, from the past which is secure. And in revolutionary science, the older theory was able to produce this and this result, and therefore the new theory must also be able to produce this or that result, from the older theory. So we have a difference here, and the difference is, of course, just the difference that before pre-normal science, there is, so to speak, nothing, but before revolutionary science, there is a phase of normal science that in the end failed to solve certain problems, but was able to solve certain problems, and therefore this revolutionary science gets a sort of orientation from this failure of the earlier phase of normal science. Okay? So that's the main difference between pre-normal science and revolutionary science. On the other hand, there are also parallels or similarities between pre-normal science and revolutionary science, and exactly these similarities we discussed a week or 2 weeks ago, namely, there is no general consensus. People disagree deeply about the way how to proceed with science and how to go about it and how to solve problems. There's really disagreement about it, and even these disagreements may cluster into schools. So there are competing schools trying to develop a certain approach, and the approaches differ, and there is no consensus about these approaches. So there is also this parallel to pre-normal science. So it's, I think, quite plausible that we have both these similarities and these differences, the differences arising from the fact that in revolutionary science there was previously a phase of normal science which is lacking in the phase of pre-normal science, and on the other hand, the lack of a consensus that leads then to certain schools, and therefore a structuring of the scientific community into schools, which is similar in pre-normal science and in revolutionary science. Okay, is that somewhat plausible, right? These are the phases you probably never experience in your own life, because it's very rare these phases of revolutionary science. And if you are in well-established areas, then the paradigm theory would say you are usually in normal science. If you look at certain parts of physics, they are really in a phase of revolutionary science. If you look at the Standard Model, then people know the Standard Model won't be the last word, because there are so many things that you cannot explain, and you should be able to explain them. For instance, one of these big accelerators now in Geneva, the LHC, the Large Hadron Collider, is just a machine that shall produce data such that some of these controversies can be resolved. That's the hope that's connected with it. Okay. All right. Now let us assume that we achieve during normal science the transition then to a new phase of, that we have a transition from revolutionary science to a new phase of normal science, because people find a new way of practicing science, and they find a new model or a new theory, a new paradigm, such that the practice of normal science becomes possible again. Then people are very happy, and this transition is then called a scientific revolution. It's really a revolution with a parallel to the political revolution, because you change a guiding framework by a different one. Right? That happens in a political revolution as well. It's a process that's not completely rule-guided. It's a process in which you have to improvise, and you try to establish a new order, so to speak, a political order or an order of normal science, and therefore there are some parallels. It's a little tricky to describe this parallel in more detail between political revolutions and scientific revolutions, but that must not bother us particularly. There are some parallels, but they are tricky, as I said. Now, this transition then to a new phase of normal science is called a scientific revolution, and that's a very interesting process, and it's a very delicate process that I'm going to describe now in a little more detail. This transition happens, as I already indicated, in analogy to the transition from pre-normal science to normal science, namely due to an extraordinary achievement. Right? It's the same that one of these schools of revolutionary science produces an extraordinary achievement such that people say, in the same way as in pre-normal science, that is probably the right way to follow for the future. Right? It's just an extraordinary concrete achievement, a solution of one of these outstanding anomalies. In the case of quantum mechanics, it was not the helium atom, that came a little later, only in 1927. But once some of these extraordinary problems, such that people believe, now this will be the new guiding framework. And this is, again, this happens in analogy to the transition to pre-normal science. Now, if you compare the old phase of normal science with the new phase of normal science, then we have a very particular and tricky relationship. And that relationship is described in paradigm theory as incommensurability. It's an incommensurability between these phases of normal science, or one can also speak about the incommensurability of the new and the old guiding theory. Now, I don't know whether you are familiar with the word incommensurability. Have you ever heard that word incommensurability? No, it comes from mathematics. It's a discovery of Greek mathematics, and it means, well, let me explain that quickly. It was a very important discovery in Greek mathematics, and it led to the exclusive development in Greek mathematics of geometry and not of algebra. People in Greek mathematics developed geometry, Euclidean geometry, but they did not develop algebra. Algebra was then a development in the Arabic countries in the Middle Ages. The name algebra is an Arabic name by origin, and that was one of the big contributions of Arabic science of the Middle Ages, that they started to develop algebra, and that was then taken over by the Western tradition, then further developed in the Western tradition. But that was, of course, in the Middle Ages, very, very important achievement. Why didn't the Greeks further develop algebra themselves? Why didn't they do it? And that was the problem of incommensurability. And the problem of incommensurability is this. If you have a square, and you look at the diagonal, and then you say, okay, I express this side here, the side A, I express with certain units. The units I take U, for instance, and then I express this by a certain number of units, say in centimeters, and then I express this, the length of the side of a square as so and so many units. So for instance, 5 centimeters, right? And then the question is, what is the length of the diagonal d of this square expressed in the same units, right? So you say, okay, this you express, you choose some units, right? Here are the units, and then you express it. So A is in this case 6 units, okay? And then you say, D is how many units? Right? That's a completely natural question. If this is 5 units, then you can ask, is that 7 units or 8 units? Or if you can't express it in centimeters, then you take a different unit, a smaller unit. Okay, and then you say, what's the number of units to express the diagonal? In terms of a units, you can express the side of a square, which seems to be completely natural, right? Completely no problem, right? The discovery was that that problem is impossible to solve. There is no unit. There is simply no unit. In principle, there is no unit such that you can express the length of a side of a square, that you can express the side with the same unit as you can express the diagonal. There simply is no unit. That's very strange. Well, we know the solution now, because the point is that d is square root of 2 times a, and that's an irrational number. Right? That's a number that's very strange. It's not a ratio between two numbers. And that means incommensurability. So incommensurability or commensurability means you have a measure, the unit, the measure for A and D, right? That would be the U. But the fact is there is no unit by which you can measure both A and D. There simply is no unit, right? It's impossible. And therefore, the relationship between D and A is called incommensurable. Incommensurable. Incommensurability meaning, it's a very simple meaning straightforward from mathematics, there is no common unit. And that's just the word. Measure is, so to speak, the unit. Commeasure means together, and incommensurable means no way, right? It's the negation. So incommensurability means nothing but there is no common measure. You know, and the unit would be the measure. If you measure it in centimeters, there is no common, so you can't express the A in terms of 5 or 6 or 7 or whatever it is, centimeters, and at the same time express the diagonal in terms of centimeters. Right? That's just not possible, right? With the n and m, and here there are natural numbers. All right? So this was the discovery in Greek mathematics, and the result was that Greek mathematics said, look, this is a perfectly wonderful straight line, right? I can draw it. So I can do geometry, right? It's no problem. This one here, a right angle here, and then I draw the line. No problems. I can deal with it in geometry. But I cannot deal with it when I use numbers. And therefore, numbers is bad mathematics, you know, because you can't even express that. And therefore, I don't want to have numbers. So the Greek decided, and that's of course a very good argument, right? It's a wonderful argument. You say, I cannot treat this damn thing here, this d, in terms of numbers, because there is no number to express it, the length. Right? There simply is no number. You can't express it in units. If you measure A in certain units, you can't express this d in terms of numbers, because, I mean, this is an irrational number, which means just that there are no, that's just an expression of that, that there is no common unit. So this was a discovery in Greek mathematics, which was, as I said, has huge consequences, long-term consequences, unbelievable, really, when you believe what happens then with the relationship between the West and the Arabic countries then, and the culture in the Middle Ages, and all that was a consequence here. The point is why I introduced that is incommensurability means, first of all, there is no common measure. Now, this term incommensurability is then transferred from mathematics here to the description of science. That is what happens in paradigm theory. The inventor of paradigm theory used this term incommensurability in order to describe the relationship between, as I said, between the old phase of normal science and the new phase of normal science. He said there is no common measure, right? And we must understand what that means, because that's a metaphor. A metaphor meaning you transfer this term from here, from mathematics, to a completely different situation, and you use the term in order to express something. And what the creator of paradigm theory wanted to express was exactly what the word says, incommensurability. There is no common measure. And now we must see what that means, right? That's not clear. You may say it's either the phase of normal science, they are incommensurable, or you may say the old and the new guiding theory are incommensurable. Is that clear so far, the mathematics stuff, and meaning no common measure, right? No common measure in which you can express both things, right? Okay. So, and the point is now, it's getting a little complicated now, but it's not in principle complicated, and simply has to be clear about these different things that are involved here. And it means a lack of a common measure, but in three different senses. Right? It's not just one sense in which normal science, old normal science and new normal science have no common measure, but they have no common measure in three different senses. And I'm going to explain to you these three different senses. And they're a little complicated, and I must give you new examples that you can understand it. Now, the first one is, and that is probably not so surprising, if you have really a new guiding framework of a new theory, then the new theory will use new concepts, different from the old theories, right? So for instance, well, I'll give you an example in a second. So we have different sets of concepts, and the point now of incommensurability is that you cannot express the new concepts in terms of the old concepts. That's the whole idea of a revolution, right? You have a somewhat radically new description of a certain area by new concepts, and if you want to understand the new concepts in terms of the old concepts, you will fail. It's just really new concepts. And you cannot express the old concepts in terms of the new concepts and vice versa. So that means we have no common measure between these concepts. They're just new concepts, and you can't express the new concepts with the old concepts. So there is no common measure in order to express these concepts, right? Now I'll give you an example, but the example unfortunately is a little difficult for you because you don't know much quantum mechanics, I guess. In quantum mechanics, you may have heard of, indeterminacy of quantum mechanics. You know that there is randomness, you never heard of it, of indeterminism of quantum mechanics at any rate. Quantum mechanics is the theory that followed Bohr's theory, and that then led to quantum mechanics. And quantum mechanics was created in 1925 and then developed until the 30s, and then it had its full form. And as I told you that in Bohr's model you have, for instance, something like the orbital of an electron. And if you look at quantum mechanics says orbitals of electrons do not exist. Doesn't exist. What does exist is a so-called wave function. That's a very abstract thing. It's a mathematical entity. Don't worry about it if you don't know what it is. It's something completely new. Quantum mechanics says there isn't an electron traveling around. That doesn't exist, right? We have a completely new conception. What we do have is a wave. A wave, right? A wave. So if you want to have a picture of it, then you may say, so we have the center around here. There is no electron traveling around the center of the nucleus. But there is a wave around a wave, right? And the wave represents the electron. It's not the electron. It's the wave that's there. And if you, I mean, this is very hard to swallow. Of course, I know. You don't understand it. And of course, many people didn't understand it in the beginning. It's mathematics. You write it down, and you write down a function that describes this wave. And quantum mechanics says the correct description of what Bohr tried to describe by the electron traveling around the nucleus, the correct description is there is a wave around the nucleus. And that wave describes the electron, right? It's very strange. Of course, it is strange. And if you don't understand it, it's wonderful, because that's exactly right? You cannot understand that in terms when you are used to thinking of an electron circling the nucleus, right? That's something you seem to understand. You say, yes, okay, I can imagine that. There's this electron, and it travels around the nucleus. Wonderful. And it's a circle or an ellipse or whatever it is, and it travels around there, and it's stable there. Yes, I get used to that, blah, blah, blah. Wonderful. And the next theory now, the next phase of normal science, people say in the new theory in quantum mechanics, sorry, there is no electron as a point, traveling around there, just doesn't exist. What is real is there is a wave, right? And the wave function is very complicated because it's a complex wave function and it's in a funny mathematical space. Don't worry about it. All I want to tell you is that the idea of a wave function, that's here, that's a very important, extremely important part of the new quantum mechanics. That idea of a wave function cannot be expressed in terms of the old concepts. It's an absolutely new concept, and you cannot understand it in terms of the old concepts. Right? That's the idea. That's the idea here, that we have a new concept in quantum mechanics, and this new concept cannot be expressed in terms of the old concepts, so we have incommensurability. We have no common measure, to express these concepts in terms of the other concepts, or these concepts in terms of the old concepts. It just doesn't work. And that's a feature of scientific revolutions, that in a scientific revolution, typically, some new concepts are introduced, and to put it somewhat loosely, and you cannot understand the new concepts in terms of the old concept. That's impossible. You cannot translate them into the old concept. That is why revolutions are so deep, because you introduce something entirely new, right? People have never dreamt of before. And you introduce something new, and the newness of, on the basis of concepts or regarding concepts is that you cannot understand the concepts, you cannot understand the new concepts in terms of the old concepts. Here's another example from electromagnetism, which is also, it's interesting, and perhaps I can just do that now for the rest of this session. And that's also something also happening in the end of the 19th century or the 20th century, and that's in electrodynamics. Now, in electrodynamics, the big discovery in the 19th century was the discovery of electromagnetic waves. We all have today electromagnetic waves. If you look at this space here, this room here, it's full of electromagnetic radiation. Not only here from the light, but also, of course, from all your handies that you have switched off, and all the television programs, and from many satellites and everything. There are thousands and thousands of thousands different electromagnetic waves in this room, right? Electromagnetic waves were discovered in the 19th century. And the fundamental idea was, when you asked the question, how is it possible that we have electromagnetic waves? How can electromagnetic waves travel through space? Which is, well, something where you say, how is that possible? The basic idea was very simple, that people said, okay, we have other phenomena of wave propagation, for instance, on water waves, right? And the water waves were quite well understood. What is a water wave? Well, you have a lake, for instance, water, and once you throw a stone in here, right, bang, then you have a wave traveling outside from the stone, right, in a circle. How does this happen? Well, it's very simple. The water is pressed here, it's pressed down here, and that water that is pressed down here is coupled with the water just next to it. So something else is pressed down here and something else is pressed down here, right? And then this one, which is pressed down here, will come back a little, right? So this one will then come back, and then this will come back, and this sort of wiggling is then a wiggling that travels outside here, right? That's the same sort of wiggling. You have a wiggling there, and because the water molecule is coupled to the next water molecule, so it gives some of its movement to the next water molecule, and this one gives it to the next water molecule, and so on and so forth. And the net result is that this wiggling in the beginning is then traveling outside, and if you have a lake, then a surface, two-dimensional, you have in water, you have these waves. If you look from above here, you throw in the stone, and these waves travel outside, right? And we have this wave traveling outside. So the basic idea here is very simple. Again, in order to have a wave that travels through space, you must have a medium, right? In that case, water. It's the water that is disturbed, and the disturbance then travels outside. That's the same with you hearing my voice. You know, why do you hear my voice? Well, we have, again, a phenomenon. It's a wave phenomenon. Here in my throat, I generate, by some wiggling. It's in that particular case, it's a vertical wiggling. In that particular case of hearing a voice, it's a longitudinal wiggling, doesn't make a difference. But the air, I'm wiggling the air, right, by talking. And the wiggling of the air propagates, because one of the air molecules are different. There are different molecules. They touch it, the next one, then the next one, and it comes to you, and in your ear it's then translated into electric impulses, and then it goes into your brain, and then you hear my voice. So the wave phenomenon, again, also in this particular case, is the phenomenon that you have a certain medium, you have a disturbance in the medium, and the disturbance travels through the medium, right? So the idea was, when electromagnetic waves were discovered, that we must have a medium, right? That we have an electric disturbance. Typically, the electric disturbance is you have a charge, right? Minus, for instance, and then you wiggle the charge, right? You play around with the charge in that way. And if you do that, then indeed you get an electromagnetic wave. So electromagnetic waves originate by moving electric charges. There we have an antenna, right? You have an antenna here, I have an antenna here, you have an antenna in your handy, and the antenna simply takes up the wave comes in, it wiggles the electrons in the antenna, and then this is translated in what you hear then in your handy. Same in television, same in satellite, and everything there. So it's always the same sort of thing. We have something wiggling, and then we have a medium, and in the medium, this wiggling then is propagated through the medium. So the idea is, of course, for electromagnetic waves, we have to have a medium, right? Something that transports the wiggling, the disturbance. So people said, yes, we need something here. It's called the electromagnetic ether. The ether in field theory. So the concept of an ether in field theory, the ether is just the medium which transports the wiggling, transports the electromagnetic field. So we need, because we have here in this, it's only air here, but air is not the medium for the electromagnetic field, it's something else, right? The air is that transports my voice to you, but it doesn't transport electromagnetic waves. They're much too fast, so it can't be the ether, it can't be that. So one has to say, yes, there must be something else, that's the ether. And it's called the electromagnetic ether, because it transports the electromagnetic waves. That was the situation in the 19th century. And it seems to be completely compelling that for the transportation of electromagnetic waves, there must be an ether, Right? It can't be different, because an electromagnetic wave is just the traveling, the propagation of a disturbance in a medium. That's just what a wave is, right? We learn that both from water waves and from noise and voices and stuff like that. So people very firmly believed in the end of the 19th century in the existence of an electromagnetic ether with very good scientific arguments. Now the point is then what happened in the early 20th century, that one could show that there can't be any electromagnetic ether. There isn't any. Right? And people, couldn't believe it. But that was really proven. It was really shown there can't be an electromagnetic ether. But it's somehow different, namely that absolutely empty space can transport electromagnetic waves. Empty space can transport electromagnetic waves. And if you followed my explanations here of waves, you must say that's impossible. I can't understand what you're talking about, right? That was indeed the case. You cannot understand, if you understand electromagnetic waves in terms of the ether, you cannot understand what the new physics after 1905 said, namely, no. Electromagnetic waves travel through empty space. No ether needed. Ether doesn't exist. Right? This is a very strange thing. And the way the puzzlement now that you may have and say, well, that's very strange, but that's completely established. No physicist today doubts that. There is no electromagnetic ether. But electromagnetic field has the property it can travel through empty space. Yeah, you have to accept that. And now you see, that's really incommensurability. That is, in terms of your earlier concept of what an electromagnetic wave is, namely the disturbance of a certain medium that propagates. In terms of this concept, it is impossible to understand the new concept. You just can't do it. But somehow you've got to get used, in the modern physics here, you have to get used to the idea, well, it's different. Electromagnetic waves travel through empty space. They do. Forget the ether. Yes? You just have to get used to this idea. And you don't get an easy picture of that, but you simply have to accept that. And that's, again, a case where you can see how strong this tension is between the old view and the new view. You cannot express the new view in terms of the old view. And that is one part of incommensurability. And that is something that has happened again and again and again in the history of science, namely that in a scientific revolution, new concepts were introduced, and the new concepts were not intelligible in terms of the old concept. And that is one of these aspects of incommensurability. Here, the incommensurability in that particular case concerning concepts, and in the next class I will show you more aspects of this incommensurability. It's quite amazing. It is something which doesn't fit your probably normal picture of how science develops, because usually you don't even hear of that incommensurability in your science education, because people don't care about this old stuff any longer because you can't understand it anyway. Okay, so that's will be the content of the next lecture, and I wish you a wonderful 7 days until I see you again.